This evening we have Ian Muirhead, and Ian is a space scientist and engineer currently conducting research into the development of very low Earth orbit telecommunication constellations at the University of Manchester, where he also lectures in spacecraft system engineering. Having completed a BSc in physics through the Open University whilst in the British Army, he left military service after 23 years with the goal of entering the space sector. He initially completed an MSc in astrophysics as a mature student at Liverpool John Moores University before returning to the OU as an associate lecturer in physics and astronomy, a role he continues today part-time alongside his primary post in Manchester, teaching PhD students and research scholarships. He is a fellow of both the Royal Astronomical Society and the Higher Education Academy, and a member of the Institute of Physics, the Royal Aeronautical Society, and the Institute of Engineering and Technology. His broader interests include spacecraft operations, space security and welfare, and the interfaces between social sciences and technology in space exploration. He is an active member of the International Astronomical Union Centre for the Protection of Dark and Quiet Skies and contributes to their policies to guide legislators, spacecraft operators, and the scientific community in the enablement of astronomy. Will you please join with me in giving Ian Muirhead a big Mexper & Swinton Astronomical Society welcome. Welcome, Ian.
Hello, yes, hello everybody. Thank you, Paul, for that introduction. It was quite a ramble there, so well done for getting through it all. Quite a long one there. Thank you for inviting me. I'm really, really pleased to be here. Good to see such a good turnout. You've got to love an active astronomical society. There's one not far from me in Heaton Park in North Manchester. And obviously, as the nights are getting darker, that's just about to start ramping up. So it's always good to see. And I just, obviously, Mexper & Swinton in South Yorkshire, I'd just like to say I did once, although I'm from the wrong side of the Pennines from your point of view, as a Mancunian, I did once live in Royston, just north of Barnsley, so up the road from you is not too far. So yeah, as was said in the introduction there, my academic background is in astronomy and astrophysics, and I do that at the Open University. But my current professional role is in spacecraft engineering and systems engineering. But because I never really want to go to the dark side and become an engineer, I do keep dragging it back to astronomy and astrophysics. And one of the big things I'm really interested in at the moment is how the advent of massive constellations or mega constellations with hundreds or thousands of satellites, how it affects astronomy in particular, but also the natural night sky for all of humanity. So that's kind of what I'm going to focus around today. I'm just going to share my screen while I remember so you can see it. 1 second. There we go. Hopefully that's popped up and you can see my title slide if somebody wants to pop them up.
That's great, thank you.
Brilliant. Yep. So what I'm kind of going to do, the talk's kind of two halves. The first half is more of a general public talk that I do to people who have no real space or astronomy background, and it's just a kind of whistle-stop tour of where we've gone in the use of space by humanity, particularly the near-Earth space. And then the second half, I'm going to flip into something that's a bit more technical and more focused on my research. There's a couple of graphs in there, but really just, I think with an educated audience, I could go a bit deeper and give you some of the background information and particularly focus on the kind of research that we're doing in Manchester and that I'm focused on in particular to try and help us through these problems while getting benefits. So my title is Mega Constellations, Starlink, Space Junk in the Night Sky. And basically I'm going to talk about the advent of mega constellations. So I shall crack straight on, I think. So I might be teaching you to suck eggs, but the space age started in 1957. And that was with the Soviet Union launching an R-7 intercontinental ballistic missile, literally a product of the Cold War, built on the technology from the Second World War, Wernher von Braun, and other scientists that the Soviet Union got. Wernher von Braun went to America. And effectively, they were trying to build delivery systems for nuclear warheads basically across the globe between the United States and America. The Soviet Union got there first, but you don't really want to launch a nuclear missile with a warhead on it. because that'll cause a war. So an alternative way of testing this technology is by launching a satellite, because it's dual use. You can use it to launch weapons, you can use it to launch things into orbit. And the thing they launched was the Sputnik, the first ever satellite in October 1957. And that was detected around the world. It flew 22 days. It was active, run on batteries, and give a little beeping signal, which I did have in the slides, but I can't hear it, so it's probably not coming over for you either. And one place it was detected was Jodrell Bank, the radio telescope, which is not too far from me on the other side of Manchester, and is actually part of the University of Manchester. And it is involved in the work that we're doing at the moment. So that was the start of the space age and the first successful launch. I think you'll notice one of the R7 rockets is one of the Lego rockets behind me as well, for those sharp-eyed. So the Americans, it caused panic. There was an idea of a missile gap, that suddenly the Soviet Union had all these rockets and America couldn't do the same thing. They had to rely on bombers. So they started to do their own program. But space is difficult, and they had a lot of problems. They had explosions, lots of catastrophes. And as you can see in the top left one that's going up there, the first rule of rocket engineering is pointy end up, fiery end down, and they got that wrong. Now, these are just the videos we get from the United States. Clearly, the Soviet Union had the same problems. They're just not an open society, or weren't an open society, and didn't display them. But clearly, it was difficult, and there was a bit of a panic. But eventually, in 1958, the first American satellite was launched. A bit of a space environment explorer, and that was their entry into the space age. This continued then into the 1960s with more and more launches. Some were crewed launches, so we started to have the crewed space programs with Yuri Gagarin, and then with American Alan Shepard, and going into the Gemini programs. But we were launching satellites, and in the 1960s, it was mainly the Soviet Union and the United States that started launching. In 1962, the first British satellite was launched, which was Ariel 1, but it was launched on an American launcher. And just an interesting fact, I love this fact about Ariel 1. So that was launched in 1962, and later on that year, it was supposed to last 12 months, and later on that year, the Americans did an exoatmospheric nuclear weapons test. They blew up a nuclear bomb in space. And that caused a radiation cloud that happened in space, and it hit Ariel 1, the first ever British satellite. So our first satellite was nuked by the Americans. But in true British fashion, it didn't actually kill it. It's the only thing ever that's been hit by a nuke and made better. So it did damage the solar panels slightly and reduce the power that it got, which wasn't a major problem. But the largest piece of damage it did to Ariel 1 was it destroyed the kill switch that was supposed to turn it off after 12 months. So the satellite actually lasted longer than planned because it was hit by a nuclear bomb, which I think is a fantastic fact. But in the late 60s, we started to do our own launch program. And in the right there, we've got Black Arrow, which was the UK's own independent launcher that we've launched from Woomera in Australia. And I do think it's got the unique characteristic of being the only rocket that looks like a giant lipstick. So we did launch them in the late 60s. And by the end of the decade, for all the space powers, France had launched at this point. China had started to test launching, but by all the space powers who were able to do it, at any one time by the end of the decade, there was about 150 operational satellites in space. So we're going to the 1970s. So that was when Black Arrow, the British rocket, launched its first satellite. So the first ever British satellite launched on a British rocket was Prospero. And that's still in space now, and it's not due to deorbit until 2070. So maybe in the future, it's something that we could collect it from space and bring back to a museum as a relic of our own history. But more and more launches were happening. More and more countries got involved. India launched their first rocket. Japan did. France did, which eventually became part of the European Space Agency. So there's more and more launches. And as satellites were going up, others were going down and failing to work. So by the end of the decade, there was probably about 300 active satellites. So you can see there's a steady progression, more and more satellites happening. We then get into the 80s, yet more launches. There was a few other independent nations that did their own launches, very minor. And then we were at about 500 or 600 by the end of the 80s. Going into the 90s, yet more launches. I put Oasis there, and then every time I see them, it hurts me because I'm Mancunian and I'm a red and they're blues. Although I did just hear their concerts a couple of months ago from up the road from me and from Heaton Park. So by the end of the 1990s, there was about 700 or 800 operational satellites at that time. And it wasn't until 2009, in fact, that we hit 1,000 operational satellites happening in space at any one time. There was more than 1,000 satellites in space because there was the dead, defunct ones, there was discarded rocket bodies and space debris, but operational satellites that were working, there was 1,000 in 2009. And then in 2019, so another decade later, we hit 2,000, so it doubled in that 10-year period. So you can see that since the start of the space age in 1957 up until the end of the 2010s, there was an increasing amount of satellites, but it was quite steady. It wasn't absolutely exploding over the 60-year period. So more and more satellites in space. But what were they going? Where were they going, and what were they doing? Is important. So there's really three key regions in space where we launch satellites to, and they're for different uses. And if you think of the Earth on the left, and then as we go towards the right, it's further and further, it's the orbital distance. So although there is no internationally agreed limit or line where space starts, it's kind of thought to be at about 100 kilometers. There's some debate around that. But 100 kilometers is called the von Karman line, or the Karman line. And it's the point where aerodynamic flight is no longer possible. If you're going to move, you have to use some kind of thruster or rocket. There's some other arguments about it being slightly higher and slightly lower, and in international politics and law dictates that. But people often say 100 kilometers is the start of space, 100 kilometers straight up. But really, most satellites have operated from 500 kilometers and above, because although that's the start of space, there is still atmosphere after that. And with the sun's energy, solar storms and solar cycles, it causes the atmosphere to expand and contract, and it causes problems for satellites that fly much lower than that. They experience a lot of drag, and they deorbit quicker. So most satellites don't really get affected by the atmospheric drag, and because they orbit from 500 kilometers ish up. And low Earth orbit is the region up to about 2,000 kilometers. So this is basically a sphere around the Earth where a lot of satellites operate. And the type of satellites that operate there, well, I've put a few pictures. So the first one I've got there is Hubble on the left. Was launched in the early 90s, had a bit of an optical fault, and then was repaired, and then had 3 other shuttle service missions, and is still operating today. One is one of the most successful satellites. It's probably the most famous satellite. People have seen the images from it, and I'm sure you're all aware of those images. The fact that this was in low Earth orbit and quite close to the Earth is the reason why it still works. The space shuttle was able to visit and repair it. That wouldn't be possible with any satellite that was further away, any telescope. And also, it would have run out of fuel many years ago if it was further away. But because it's very close to the Earth, it's able to use the Earth's magnetic fields to do its aligning and pointing. So that's why Hubble's still operating, is because it's very close. Next on the right is a European Space Agency satellite, and effectively this is Sentinel-2. So this is an Earth observation satellite. And unsurprisingly, you've got telescopes pointing up, you're looking at stars. If you've got cameras on satellites pointing down, you're looking at the ground. It's the same principle. And the closer you are, the better resolution pictures you can have with the same camera. So we like to put a lot of Earth observation satellites quite close to the Earth in low Earth orbit. And at the bottom one there, again, you probably recognize it, is the International Space Station, first occupied in Halloween 2000, so 25 years ago, just under. And that was the last time when there wasn't a person in space. So before there's been somebody in space, consistently, a human in space, since Halloween 2000. And the Chinese have a space station called Tiangong, and there's going to be commercial space stations happening soon. So it's possible, I'm not going to bet my life on it, but it's possible that we may never again live in a time where there isn't a human off Earth, where all the human race is on this planet, which I think is quite an interesting fact, and I hope it continues. So that's where a lot of satellites are and the type of use they have. Then just beyond there, then 2000 is a thing called the inner Van Allen radiation belt. And these are the magnetic belts around the Earth, represented here by a particularly mischievous cat waiting to whack any satellites that fly there. And is an area of high radiation. It captures particles from the solar wind and extragalactic wind as it comes into the Earth environment. And although you can transit through it, it's difficult to fly a spacecraft in it, because over time, the amount of radiation buildup would damage the components without heavy and difficult and expensive shielding. So we don't tend to operate satellites in that area. So the next area then is medium Earth orbit, from about 10,000 to 25,000 kilometers away. And the vast majority of use for here is for position navigation and timing. And the most common one you've probably heard of is GPS, which is the American system. It's got about 32 satellites out in there. But there are lots of other versions. There's a Chinese one called Baidu. There is a Russian one called GLONASS, a European one called Galileo. There are also very much smaller ones from Japan and India, which are more regional rather than global, but they're effectively allowed to tell your position. And we use them for driving. I'm sure you've all used Google Maps when you're driving a car and you set your GPS on. Well, this is what it tracks. Your pizza deliverer when he's coming down the road with your Domino's, and you can see him coming, is using that technology from space. So that's a really important use. You know, it's used everywhere and it's become integral to our lives. But another thing we get off that is a single unified clock timing. So the time comes from satellites, from the atomic clocks. And that allows a lot of the financial systems to run. When you get money out of the cash machine, the time comes from a satellite to make sure you don't take money out of one cash machine, then out another one and say, oh no, I haven't done it. So your balance is updated. But also a lot of financial transactions are done by computers, and they're done extremely fast in the stock market. So they need to be accurate timing. An interesting thing with the global positioning systems is all the satellites are moving, and the Earth's moving, and everything on the Earth is moving. So it's quite difficult to get a single coherent frame of reference for you to put everything on. If everything's moving, what is the 0 point, effectively, the set point? And radio astronomy, it turns out, is essential to that, because the best way to get a single coherent point is to look at something that's extremely distant, like an extragalactic quasar that's well beyond our own galaxy, that's effectively stationary from the point of view of everything in the solar system. So distant extragalactic radio astronomy is used as the fixed stationary point for all positioning. So when you order a pizza or your Amazon delivery driver comes, they're using the technology provided by radio astronomy, which again, I think is an excellent use. And then beyond that, then there's another radiation belt, another mischievous cat there that's ready to damage your satellites. So we don't really operate things much beyond 25,000 kilometers until we're outside the Van Allen radiation belt. And then there's a very unique place, and it's called geosynchronous orbit. It's a very specific point of just under 36,000 kilometers away. And the reason why it's not a range, why it's so specific compared to the others, is that this is exactly the point where it takes 24 hours to orbit the Earth. So if you've got a satellite there, from the point of view of the ground, it's fixed in the sky. So your satellite television uses this. This region, this is where a lot of communication satellites traditionally were, and certainly a lot of television and media satellites. Whenever I'm watching Gary Neville tell me how terrible Manchester United are, again, it's coming through that satellite from out there. And the satellites, because they're outside the Van Allen radiation belts, are in quite a harsh environment. So they need to be robust, and they need to last a long time because it costs a lot of money. They cost billions to build and put there. And some of them are massive, the size of school buses. So the picture I've got there is actually a really interesting one. So it's from an experimental vehicle. That is a communications satellite, an American communications satellite. And it's a real picture, which means there was another satellite further behind taking that picture. And effectively, it was an experimental satellite that was launched to refuel that satellite 36,000 kilometers away from the Earth to extend its life. So rather than build a new satellite and launch it out there, they're just refueling and keeping the same satellite going for 15, 20 years or longer because it's doing its job. Why do you replace it? So that's the kind of technology that's being developed. So they're the three key areas around the Earth where services come to the Earth. And our economy is built upon this. It would cost our country billions every day if GPS stopped working. It's integral. It's all the services you don't see. Communications use them. And up until 2019, when I said there was about 2,000 satellites, the distribution of satellites between these three were about half in low Earth orbit, about half in geosynchronous orbit, and then a small scattering in medium Earth orbit, the remainder. So that was kind of the separation. And the reason we had a slow increase was because of the costs of launch. It was very expensive. So I've got a picture here is of Artemis, which is this is the Space Launch System. So this is the new NASA moon rocket that's going to return humanity to the moon. So since Apollo 17 in 1971 or 2, off the top of my head, there has been no human gone beyond low Earth orbit. Nobody's gone to the moon or beyond. This is how we're going to return to that. There was the test of the rocket uncrewed. And in fact, the other day, NASA announced that they're planning for the first crewed test, which will be a raw orbit around the moon and then a return to the Earth. With a crew, 3 Americans and a Canadian, should happen sometime early next year. They're aiming for February next year. So interesting. So this is basically the new modern Saturn V moon rocket. But the problem is you've got this massive rocket that's as big as a tower block, and all you get back is this tiny bit because you have to it costs so much to get to the speed you need. It's about 15,000 miles an hour, about 25,000 kilometers an hour to get into Earth orbit. And then never mind getting into escape to go beyond that. And the higher and further you go, the more energy it takes. So if you go into geostationary orbit, it takes more energy. And it's the same for satellites. That tiny satellite is all that's left after these large rockets. So effectively, every time you launch, you're disposing of the rocket, you're throwing it away. And if you think of the cost of having to do that every time you took a flight somewhere, you had to build a whole new plane, you'd certainly fly a lot less. People recognize this, and the space shuttle was developed to be reusable, and it landed like a space plane, and they tried to refurbish something. Understandably, because it was the peak of 1970s technology. Ultimately, the costs to refurbish the space shuttle, they may as well have just built a new one, so it didn't actually make any cheaper. But there were attempts to build more traditional rockets rather than space planes that could land and be refueled and reused. And on the bottom right there is an experimental called the Delta Clipper, done by Douglas, an American company, in conjunction with NASA. And this is a collage of pictures of it taking off, moving across a position and landing. And this was about 4 or 5 meters tall, so not massive, but was a test device. And this, I think it was 1994, these pictures were taken. So we started developing the technology to be able to reuse launchers and hopefully make things cheaper. But the Cold War had ended by that point. The International Space Station was costing far more than it was supposed to. The Space Shuttle was costing far more than it was supposed to. And NASA's priorities were just, we have to spend the money on something else. So they cut that program, but the technology did work. It was a potential path. So the next stage then went to private industry. So I'm sure you've heard of SpaceX and Elon Musk. So his goal, he actually hired a lot of people from NASA and from Douglas that had done these programs earlier, got the technology. You know, when he says it's a private company and they're all super geniuses, well, most of it was funded by the US government. So like most private companies, they're relying on state enterprise. And started to build a technology, and they built a rocket called the Falcon, and then they developed that, and they built another version called the Falcon 9. And the point with the Falcon 9 was they wanted to be able to land the boosters. So instead of landing like a plane, it's like a firework landing backwards. But it didn't go quite to plan at first. So again, the first rule of rocket engineering, points end up firing down, didn't work. This one had a broken leg. It did land and then broke over, so didn't survive the landing. This one ran out of fuel a few seconds before the bottom and then collapsed and exploded. So we had lots of problems, lots of failures. But on the 20th flight of a Falcon 9 in late 2019, I think, it landed on the first ever landing of an orbital class. And then in the following year, I think on the 23rd or 24th, it landed on a barge. And then a couple of years later, they launched a heavy version, which had strap-on side boosters, and they both landed together, which for me is the most Buck Rogers futuristic thing I'd ever seen at that point. There's two effective towers, rockets landing backwards on the ground. So what this meant was, although the second stage, the upper parts were still getting wasted and thrown away into space, the bottom stage, the first stage, which ultimately has to get you through the thickest part of the atmosphere and the strongest gravity, get you to the first part of the speed, were able to be landed, refurbished and reused. And it was effective, unlike the space shuttle, it was cheap. So what this meant is suddenly launch became a lot cheaper. And to give you an idea, it was $35,000-ish for every kilogram into space on the space shuttle. Most of the launches were somewhere between 15 and 20,000 kilograms into space. And this is a Falcon 9 launching, or 3 different sites of a Falcon 9. And this dropped the cost of something like $2,000 or $3,000 per kilogram. So up to 10%, up to an order of magnitude cheaper. 10% of the cost. So suddenly, if it's cheaper to go into space, you can start thinking about spending money and putting more satellites up than you could do before. At the same time, there was an advent of mass production in spacecraft development. Previously, every single spacecraft was effectively unique. You build 1, 2, certainly not many more than that. So they're unique. So you didn't have mass production. They were often quite laboratory built. And that's still the case for some satellites today. But what SpaceX did was add mass production and industrial techniques and started building dozens and hundreds of identical satellites. And this is the Starlink telecommunications satellites, about 25, 30 of them there, all being launched at the same time from the upper stage. So suddenly you've got lots of satellites that are cheap to make. It's cheap to put them into space. So your access to space is suddenly much easier, which was the big barrier. So why are they doing it? Well, what we have here is a bit of a cartoon showing the Starlink constellation. So rather than having 1, 2, or 3 satellites, they decided to launch hundreds and thousands of satellites called a mega constellation, much lower in order to provide telecommunications. So when I talked about the orbital regions where they go, the geostationary region that's 36,000 kilometers away, because the Earth's a bit squashed on the poles, you can't really see them. But if you space 3 satellites at geostationary equally around the Earth, you can see everything on the Earth except the poles, so you can provide worldwide communications. But it is quite far away, and although light's fast, if you have to go a round trip from me to the satellite to the ground, back to the satellite, back to me, altogether the round trip conversation takes about half a second, which in computer time is quite a long time. Whereas if you go much closer, the round trip time for your electromagnetic signal is much shorter. But because you're much closer, you now need thousands and thousands of satellites to provide coverage. And sometimes if you want a lot of users, if there's a lot of people under the satellite, one satellite won't be enough. So you have to see lots and lots of satellites in the same area. So they effectively designed a constellation of thousands of satellites and started launching them. And the reason they did this was to provide fast internet, as fast as you get in your house, but from space through a basic dish. There's a picture of a dish there in the top right. That's one of the early versions of the Starlink dishes. And the dish costs about $400 or $500, and the subscription costs about $75 or $80. And suddenly you've got super fast internet almost anywhere. And things it's been used for, on the top left picture on the right hand side is a school in Africa. So remote, far too remote for infrastructure and for fiber optic cable, suddenly could have access to internet. On the top right hand side then is Ukraine. This is in a city in the east that had been attacked, had all its power knocked out. Obviously, they're in a war-torn country. Certainly early on in the conflict, it was much worse in some parts than it is now. And those refugees moved across the country, and there was no way of them getting communications. Whereas if they put that dish out, connect it to a Wi-Fi router, and you connect your phone to it, suddenly you can send messages. And I'm sure you can imagine what a godsend that was to people in Ukraine during this difficult time. In the picture on the left there, it's said about Iran. Some were smuggled over the border. They're actually banned in Iran, but then they were used to provide organization for people who were fighting against the regime there. And of course, because everything's about consumerism and making sure you can see pictures of cats no matter where you are, there's somebody at the bottom right there who wants to get away from the world, wants to be completely isolated, away from society, but still needs to have a laptop and connections to the internet. So they can have that too. So lots of uses. And I think it's hard to underestimate how important this technology would be if you had global connectivity, if you could connect everything up, not just people in the things I've spoke about, but automation, monitoring of the seas, things like driverless cars, all that kind of stuff. So the ability to have a ubiquitous communications network is really going to be important for our world. But it comes at a cost. So as I said, we've developed over time, and it took 52 years to get to 1,000 operational satellites at any one time, but only 10 to double that by 2019 to get to 2,000. And there are only 5 to double it and double it again. So last year there was 8,000 satellites. I actually checked this morning, and there are just over 13,000 operational satellites as of this morning. And that's because of the cheap launch. That is because of the cheap launch. And in fact, SpaceX are launching so regularly now that when I, this afternoon, went to check when their last Starlink launches were for this communications constellation, there was one at 8 o'clock this morning, UK time, and the next one tomorrow is at 5 o'clock tomorrow morning. So in 24 hours, there will be 2 launches, each with 20 odd satellites in. So that's an amazing rate of replenishment. And that means our space is getting crowded above us. But what's the future going to look like? What's launch going to look like to the future? So the Falcon 9 is just a normal rocket with a payload of about 26 tons, and it launches something like 20 to 30 of these communication satellites at any one time. The next stage of development is called a reusable super heavy vehicle. So what I've got here is this is a test vehicle. It's a prototype. It hasn't been successful in orbit yet, but it's done a number of suborbital tests, and it's called Starship, very originally named there. And it does look like something out of Buck Rogers, and it's a two-stage super heavy vehicle. It's hard to gauge it, but if you think of the size of the Apollo moon rocket, the Saturn V, this is bigger and more powerful. And it comes in two stages, and its payload capacity is, when it works, expected to be 100 to 150 tons. So maybe 5, 6, 7 times more, able to launch hundreds of satellites at one time. And even more than the fact that it's got such a capacity is the fact that it's aimed to be fully reusable. So the two parts of the rocket, on the left-hand side is the test of the booster coming back down. And on the right-hand side is the upper stage, which is landed in the Indian Ocean as a test. And you can see it lands on its bottom end. This is it ditching into the sea. So they can recollect and refuse that. Eventually it'll land on land. The left-hand one, the booster, the first stage, the tower it launched from has these arms. They call it Mechazilla. Again, proper grown-up. These arms have come closer there on the landing, and like chopsticks, they catch the booster in the sky. And again, it's hard to underestimate. This is like a tower block, like a skyscraper, coming down from the sky of rockets and being caught in midair on the launcher it came from. And the reason they catch it in midair is so it doesn't damage the landing pad. These arms can then drop it down on the landing pad, refuel it, stick another upper stage on top, and launch it again rapidly. So rather than every day, this could be every hour. So you think of the quantity we can start to move into space is going to be spectacular. Good and bad sides to that. One of the bad sides is the amounts of satellites that we're going to proliferate, and perhaps even the size. Maybe we're going to start in bigger and bigger satellites. So there's been some research done by a few people in 2023. So this is 2 years old. That with the International Telecommunications Union, where you ask for frequencies to be able to transmit on your satellites, there has been requests for 1 million satellites to be launched by 2030. So we're on 13,000 now, and there's been a request for 1 million by 2030. Now, I don't think 1 million will be launched by 2030. There's some very spurious requests. So the country of Rwanda, not known for its space program, has asked for a constellation called Cinnamon of 400,000. So they're the biggest one. They're never going to launch one, never mind 400,000. Effectively, that's a way of grabbing spectrum that they can sell to somebody else. But most people who are interested in the space sector think we'll probably get to at least 100,000, maybe 300,000 by 2030, which is only 5 years away. So that's, again, another exponential increase of satellites in space. So what are the problems, and particularly what are the problems for astronomy? You were talking about your observation sessions last night, and you're going out again tomorrow. And I'm sure you've seen the satellites passing overhead and the streaks. And this is clearly one of the biggest problems, certainly for optical astronomers, and also for naked eye observations. Satellite streaks are becoming more and more common. I was cycling to work and went out early the other morning, and I saw one satellite. And when my eyes adjusted, I then saw about 30 satellites, and they were in counter-rotating planes. So that was the Starlink planes going overhead. And although it might be interesting seeing a couple of satellites in the sky, we don't want the sky to be full of satellites. And not just for astronomy. There's a lot of cultural practices around the world that use the sky. Tourism, ecotourism, and dark and quiet skies tourism in remote places is really useful. It's actually really useful for poor and developing people to make people stay because they've got a reason they can run it. So it's good for development effectively. And there's even thoughts that if there's so much moving light in the sky, that it could affect both humans, our balance and our orientation, but also the migration patterns and the behavior of nocturnal animals, so affect their own world just by having these satellites in the sky. And again, I'm sure you've seen it in your own pictures as an astronomical society, but the trails over longer exposures then build up and build up. So these particular video and picture was from a university in Canada, and it was a meteor tracking Canada, but it tracked all these satellites overnight. And in fact, because of the altitudes of where these satellites are, and Hubble Space Telescope being slightly lower, it's even affecting space-based observatories near Earth and tracking across them. So you're losing science, and people have paid millions and billions for these facilities, particularly the professional facilities on the Earth, stuff like the New Vera Rubin telescope, which will probably be most affected. Over in Chile is being built at the moment. It's going to be hugely affected by these satellites. And it's not getting any better. So I've said a lot about SpaceX, and I've said a lot about the Starlink and their launches, but ultimately they're just one company and they're just the first. There are lots of other companies building launchers. So Jeff Bezos and Amazon are building another super heavy launcher for their own constellation. Plus, the Chinese want a reusable rocket. The Russians, everybody wants one. And there's a lot of companies wanting to build telecommunications constellations. Now it's cheaper. The reason I've highlighted AST here is they are designing something called direct-to-device communications, which is probably going to be the biggest driver of satellites in coming years. And this is to connect your mobile phone to the sky. So when you haven't got connections in a local cell tower, you connect from your satellite in the sky and you've got coverage everywhere on the planet. And there's different ways of doing it, but the way they're doing it is with a massive high-powered phased array antenna. And this is the largest antenna launched into space. It's 64 square meters. There's currently 5 of them up, and they are the brightest thing in the sky. So they're about magnitude 0. So certainly as bright as the brightest stars. And they plan for a constellation of about 250 of them, and their phase 2 is 4 times bigger. So it's over 200 odd square meters. So these are massive, bright satellites. Going to be a real problem. And again, these are just a couple of companies. There are dozens of companies, dozens of constellations. Beyond the optical, then, beyond the visible, radio astronomy is important. And I've said it's important for GPS. And at the top there, I've got a bit of a graphic of LOFAR, which is a radio astronomy receiver in Holland, or this is the one in Holland. There's a few around Europe. And the little red dot there is a Starlink satellite going over the sensors being modeled and being detected. But again, I said there'd be some graphs, a bit of science in there. So what we've got a graph here, then along the bottom is the observation time. It's 3,600 seconds or an hour. And then on the left here on the y-axis is some frequencies. And it's important to note that these frequencies are radio astronomy protected frequencies that nobody is allowed to transmit in. So this radio telescope in Holland monitored for an hour these frequencies to see if there was any signals, and they detected signals. And they detected signals when the Starlink satellites were going overhead. And all the signals in the red box, the size of the circle that you're seeing in the red box, are effectively the strength of the signal in the rather odd unit called Janskis. So they were detecting these signals. What these are emissions from the satellite itself. So everything electronic emits, the power cable charging your phone emits, everything provides an electromagnetic signal, and it's uncoordinated. It's not modulated in any way. It's just a random signal noise created by the passing current. When you launch a satellite, there are rules about electromagnetic compatibility to make sure it doesn't interfere with anything. But there's really only 2 things they care for. One is, will it affect the launcher? The spacecraft is normally turned off or mainly turned off. So the rocket that's taken it to space shouldn't be affected, but they do test on anything that will be turned on. And then when it's in space, it's very far away, and these signals are quite weak. So all they really care about is it's going to affect itself. They don't want the heating system to affect the communication system or something like that. So that's all they test for, and that's all they have to test for before they go to space. Historically, if there was any leakage from the spacecraft that was being detected by radio astronomy, because radio telescopes have to detect very faint signals from very, very far away objects, that satellite would have a unique signature, because like I said, only a few of most types of satellites were built. It would pass over infrequently, so you might be able to ignore it and it wouldn't come over again for days, weeks, or months. When you've got thousands and thousands of identical satellites leaking the same signal, suddenly you've got a constant background noise, and that's what this is. This is just leakage from inside the satellites that's affecting radio astronomy. And then the blue area there, this is a slightly different signal, and this is for satellites that are operating lower. And when they first launch out of the Falcon 9 rocket, they look like the right-hand side, which is the open book, where the solar panel is flat against them. And the little rings we've got inside the blue box, this is a ground-based radar. It's called Graves. It's a French space radar, military radar, bouncing off the satellite and coming back down. So although the radio telescope is well over the horizon from this radar and shouldn't be affected, it's happening. So just the existence of these satellites is causing a problem for radio astronomy. Beyond this, then, beyond the satellites I said for communications, the cheap launch means they can start doing other things in space, and there are lots of plans to do other things. A really hot topic, which the UK are involved in, is space-based solar power. So it's inefficient to have solar panels on the ground because of the atmosphere being in the way and the Earth rotating, going in the dark. So the idea is you put solar panels in space, they get constant sunlight, they collect that sunlight, convert it to microwaves, beam it down to the Earth. The idea initially is to put, well, the big goal is to put massive satellites at geostationary orbit, so they're over the same place, so they can provide a constant stream of power. And these objects are 10 kilometers wide or bigger. They'll be the biggest human-made objects ever, and we're going to build them nearly 40,000 kilometers away. That's an amazing technical undertaking, but you've also got a huge reflective mirror suddenly in the night sky all the time is a problem. Clearly, that is a difficult technology to do. So there's other ideas and other proposals to build mirrors in space that operate low, which means you've got a constellation, a lot of them, that reflect sun down to solar panels on the Earth and just provide sunlight through time. Again, these are terrible ideas that are going to be a real problem for astronomy if you're beaming sunlight down from space at night. But they are real ideas and they are getting real funding. So they are a challenge to astronomy. Beyond that, there's proposals from companies to do space-based advertising. So using lasers and satellites to project images into the sky. Again, an absolutely insane idea, but it's getting funding. People think they can make money out of it, and cash is unfortunately king. So just as a mock-up here, can you imagine your night sky suddenly turned into this? And you've got Starbucks glaring down at you instead of looking at the sky. We'd lose the night sky forever for humanity. So clearly these aren't good ideas. These are a problem, and we've got to see how we can do it. Some of the ideas are terrible that I don't want to happen. Stuff like the space-based advertising, we just don't need it. But some of the technology will really help parts of the world. So we've got to try and find a way to peacefully coexist without destroying the night sky. And this is where I kind of come into my research. And what we're doing. So my group in Manchester are looking at very low Earth orbit. So when I spoke about the different orbital bands, I said 500 kilometers above, because you're not really affected by the atmosphere. There's a region called very low Earth orbit, which is below 500 kilometers, where you can fly satellites, but you've got to consider and you've got to change your mission and do things to be able to survive. And again, that's because of the atmospheric drag, but it's also quite a good radiation environment, and it's easier to get there because it's cheaper to launch there. And particularly for the UK, we've currently got proposals to have launch from the UK, from Shetland and a few other places, particularly northern Scotland. And these are small rockets, so economically could be good for the UK if you're launching into lower orbits. And the type of satellites they've launched, there's the few on the right-hand side there, and they have to operate in a certain way in very low Earth orbit, and they've all got very similar characteristics. The first thing is they're quite streamlined and aerodynamic, which you don't normally have to do for a satellite. You can build it like a brick. But because it's going through the upper atmosphere, you want to reduce the amount of material that's hitting the satellite. And particularly the top two have also got electric thrusters. So these are low power thrusters, propulsion, but they allow it to mitigate against the energy it's losing from any atmospheric drag. So they only provide low thrust, but they provide a lot of thrust. So the top one flew really close to the Earth and measured the Earth's gravitational field, Goche gravitation field. The second one holds the record for the lowest operational satellite. It had to fire all its thrusters and everything, but it managed to complete, I think, a full day orbiting at just over 100 kilometers. And then the bottom one is an experimental one that we launched and operated from Manchester. And we're trying to work out how we can operate in these lower orbits. So there was a European consortium to work out how we can do it with a number of different universities, including Manchester, and our big partner is Stuttgart in Germany, and they're kind of like the center of a lot of this research. And we built SOAR, the satellites for orbital aerodynamics research, and this is a video of what the satellite looks like when it's extended. They look like solar panels on the side, but they're not. Each of them wings has different types of materials, and the aim was to test the materials in orbit and see which reduces the drag and which makes it worse, special materials. And then at the front was a mass spectrometer, and we also had axis measurements. So if we put just two of the panels out and we test the materials and the whole attitude, the direction of pointing of the spacecraft changed, we'd know that that was effective. We then measured the change with a different material, and whichever was more or less would say whether the drag was worse or better with that material. And we measured the amount of rare atmosphere that we'll find in there. So this was our spacecraft, and it launched in June 2021, again on a Falcon rocket. This was a transporter rocket to the International Space Station. And then when it got up to the International Space Station, about 2 weeks later, they had their small satellite launcher, which threw it out into space, launched it, and you can see it getting winged out there before it's got any extended wings. And it operated for about 9 months, controlled from, this is Schuster Building at the University of Manchester, so we controlled it from our own facilities. And after 9 months, it got lower and lower. It didn't have propulsion on board, so the drag of the atmosphere did make it lower and lower. And eventually, it completely burnt up in the atmosphere. And that was the end of the mission. And we got some really good information on different materials to reduce drag to allow you to operate for longer. And that's useful because you can start doing cheaper missions and get better missions in smaller satellites, so they're less wasteful. And to give you an example, this is one of the training complexes for the Qatar World Cup, and it's exactly the same camera as if it was imaged from two different altitudes. So 650 kilometers, the resolution's quite blocky. You half that to 325 kilometers, and suddenly you've got a much more clear Earth observation picture. So it's the same camera, closer, better resolution. A lot of what I work on is then telecommunications, and the vast majority of satellites in space are for telecommunications. And the link budget, effectively, the amount of power and parameters you've got to use to communicate to the ground is just easier if you're closer. It doesn't take as long. There's less loss in the distance. You're actually below some of the atmospheric layers that interfere with it. You can have smaller spacecraft. It's quicker. So if it's less latency, suddenly if I press something here and you're in America, you get a much quicker response, and that's useful for things like remote medicine, remote surgery, driverless cars, being able to react quickly to some information that's being reported through a satellite network. And again, financial transactions, if you can get a millisecond quicker, you make more money than the other person. So there's always a financial driver there. But also spectral efficiency, there is only a limited amount of radio spectrum. If you're lower, you reuse the frequencies more and get more spectrum efficiency. So it's really good for telecommunications. But the satellites are moving really quickly. You have lots of them. You need more of them. The Doppler shift, there's loads of technical problems around it as well. But if you're lower, instead of having space junk left in space, so Sputnik, the first ever launch, was labeled 1957A. It was A being the first one in 1957. There was also at exactly the same time 1957B and C. B was the upper stage of Sputnik, and C was the shroud that covered the satellite. So we launched one satellite and two pieces of space junk. If you're lower, the atmospheric drag removes satellites from orbit quickly, and it kind of like self-cleans. The rules at the moment say 25 years after you finish using a satellite, after 25 years, it has to be removed from space. But they're changing that because it's just too long. So it's now being changed to 5 years. But if you're operating in lower orbits at 450 kilometers, it might take a little over 5 years for it to deorbit with no action at all. Just fly in, the drag will bring it down in just over 5 years. But as you go lower, it gets quicker and quicker and quicker, all the way down to a day at 100 kilometers. So you turn off your electric propulsion, you point your satellite so the broadest area is in the direction of travel, and your satellite deorbits, and that's the end of that. Clearly, if the satellite's a bit big, it might deorbit into the ground. It won't all burn off in space. Hopefully, most of it does. But what we do is the place called Point Nemo, which is the furthest point for human occupation in the South Pacific Ocean. It's the satellite graveyard. It's where we put satellites that we know aren't going to burn up in the atmosphere. We crash them there. And in fact, that's where they're going to crash the International Space Station, probably in the next 5 years. Which again, I think is a great shame. I think we should be raising it higher and using it as a museum piece in space. If we've got this cheap launch, maybe we should make some use of it, but who am I? So that's a good thing, assuming you accept that burning up satellites in the atmosphere is a good thing, which traditionally we did. But now it's being questioned because the amount of material that's going in there and the types of material is causing yet another climate problem, a bit like the ozone layer, where we had CFCs that went into the ozone layer and it was materials that weren't normally there. Well, actually, maybe burning spacecraft into orbit is not a good idea. So there's challenges too, but at the moment, this is the best way to clean space. And I'm just going to finish up then on my current research. So I'm looking at the dark and quiet skies of operating lower and what that means. And for optical, visual observations of satellites, ultimately satellites, other than the International Space Station, don't have lights on them. They don't flash in the sky. The thing you're seeing is reflected light, most commonly from the sun. There is some earthshine as well. So if they're in the Earth's shadow, they are effectively invisible. An important fact is that lower satellites darken more quickly. And I've just got a graph that I plotted here on the right. And again, I'm sure you know the terms that as the sun angle drops and the sun gets below the horizon, you get into nautical dusk and then astronomical twilight. And then from astronomical dusk, you go into true night. Then depends whether you can see point or diffuse sources. So that's when most astronomy takes place. So if you're very low, so the altitude is along the bottom here with lower to left. If you're in the very low area of space, actually half the sky, so from the point above you all the way to the horizon in the direction away from the sun, every satellite will be dark from that point for the very lowest satellites. But before nautical dusk. So effectively, you won't see them. To get higher, before you get into true night and at the end of astronomical dusk, it's about 335 kilometers for half the satellite. In fact, satellites above 30 degrees, so when the air mass is twice what it is at zenith, the very, very lowest satellites are completely dark above 30 degrees. But at 200 odd, you've got half the sky there. But for the naked eye, so that period that between the horizon and the direction of the sun and 30 degrees above it, that's where you will see the majority of satellites, like literally thousands of satellites if they all go up. And they are never dark by astronomical dusk, but the lower they are, the more sooner after astronomical dusk they're dark. So lower is better because they go dark quicker. And also, if you're using detectors and you're taking long exposures of these satellites, they transit across the field of view more rapidly, which means they have less time to build up on the detectors. So even though they're brighter because they're closer, they actually have less of an impact even when they're illuminated because they're over the detector much quicker. And there's work happening on reflection materials and offsetting the solar panels so they don't direct towards the observer on Earth, painting certain parts dark without making the satellite overheat, using different mirrors, stuff like that. So we're trying to make them effectively invisible to optical. So that's what I'm working on. Beyond the optical, if it's infrared, well, effectively it's a warm box at room temperature flying above. And if you bring them closer, that means you've got a warm box that's closer and it brings a bigger signal for infrared, near infrared observations. So maybe you have to do some kind of shielding in the Earth facing direction for that. Radio is going to be a problem though, because that signal that's leaking is now closer and stronger. So we're going to have to mandate testing on Earth so we can characterize what the signatures are that they're emitting, and then maybe better shielding on board, which again comes with a cost, because if you shield something, it costs mass on the space that you've got to launch in there. But launch is getting cheaper, so maybe more viable. So there's problems, but ways of trying to resolve it. And then just to finish up, then the latest work that I've done is the latest version of Starlink, which is planning 30,000 satellites. About 10,000 will be to deliver satellite internet, above 500 in traditional low Earth orbit. But they're also trying to do direct to device, so again connecting to your mobile phone, and they're looking at 20,000 satellites orbiting between 320 and 360 kilometers. So again, this is within very low Earth orbit. On the right there, I've done a bit of modeling. So the left-hand graph is how many satellites you will see above the horizon, and at the peak latitudes, so about 35 degrees latitude, which is not far from the Canary Islands and Chile. So where a lot of observatories are, there will be about 1,200 of these satellites visible in the sky or within line of sight at any time. 90% of them will be below 30 degrees. So there'll be a band of satellites along the horizon. Above the astronomical horizon, so 30 degrees elevation above the horizon, the worst it drops to is about 120. And without going into too much detail, although there are twice as many very low Earth orbit satellites, they have proportionally less of an impact. It's the higher ones that you see more of. So lower ones you see less of, even though there's twice as many. And then for the coverage of the satellites, what I've done here, I've just modeled the satellite coverage, 120, the peaks put over a map on the Earth, and you can see the deep red bands cover the United States, Europe, Northern China. So when they talk, if you ever hear them talking about we're going to connect the world and we're going to help every school in Africa, it's true they can, but I think it's quite telling that if you model what their actual satellite coverage is based on their design, is that most of the focus of satellites are over areas where people have more money in the United States, can pay for subscription, and they've got less satellites on them famously low population places like Brazil, Nigeria, India, Indonesia. So clearly they're not that bothered about places where there's lots of users who don't have internet. They're more bothered about lots of users who have money. So interesting analysis. And then just if you fancy a bit of a read, just a couple of weeks ago, I had a publication about this model that was released in the American Astronomical Journal, where I looked at the impact on optical astronomy for these. So just going to finish up then and open up for questions. But just to summarize the talk, the use of space is vital to humanity, and we've developed quite slowly, increasing the number of satellites in the sky. And early on in the space age, it wasn't really thought to be a problem because you'd have intermittent satellites. But with cheap launch, with reusable launch, with mass production of satellites, Suddenly you're getting hundreds, thousands, or potentially millions of satellites launched into space. And that's a problem for Earth, and it's particularly a problem for astronomy, where you're going to have these satellite trails going across. And then in Manchester, we're trying to look at operating satellites lower to try and mitigate this and also get better uses and try and balance the challenges that this causes for astronomy and other sciences, along with getting the benefits. There are going to be some great benefits of it, not just Elon Musk making money. So I'm just going to finish up with my favorite picture, Van Gogh, Starry Night, painted in 1889, looking over the fields of France and seeing the stars in the sky with his own unique eye. And then I'm going to go to my version, Starry Night 2089, so 200 years later. I hope a new Vincent van Gogh doesn't have to paint this with satellites passing across the sky, ruining what is a natural resource for all humanity. And they never asked our permission to ruin it. That's the end of my talk. Thank you very much for your attention. This is me and my LinkedIn and email if you want to follow up on anything after. But that's the end for me. So I'm happy to take any questions or chat through any points or anything really.
Ian, thank you for a very thought-provoking talk. I'm sure that people will have questions and comments. I was going to just ask you to stop sharing, and you've already beaten me to it. So as usual, ladies and gentlemen, if you're online, put a digital hand up, please. If you're in the room, then get my attention, usually with a £20 note. That usually does it. Okay, so online, Mike Scollin.
Hi, Ian. Thanks very much for the talk. You were talking about the cost of putting this tiny little bit on top of a rocket into lunar orbit, effectively. Has any consideration ever been given to reusing that tiny little bit on the top, putting it back in Earth orbit and refueling and reusing as a kind of lunar shuttle?
Yes. So when I was talking in the talk, I used the Artemis moon rocket at that tiny little bit at the top, but effectively until the Falcon 9, every rocket does that. Every single satellite that's gone into space has effectively thrown away the rocket and that last bit's on the top. What's traditionally happened with the spacecraft around Earth is if they're near Earth, we just deorbit them in the atmosphere and declutter it as best we can. But that doesn't happen for ones that are quite far away. And there's never been a rule or any way of enforcing a rule to make people get them out of space. So like I said, the Prospero spacecraft launched by the UK in 1971 will be there till at least 2070 based on the analysis. So there's all these satellites and there's literally thousands of old rocket bodies and defunct satellites that are still in space. If they're further away, if they're at geostationary orbit, you can't really bring them back to burn up in the atmosphere. So what they do is they push them into, it's called super geo orbit. So they just push them just a couple of 100 kilometers beyond the orbit, and they reckon they'll stay there for thousands of years, which is great until it's a few thousand years have passed. And our ancestors are now like, what's all this space junk coming back down through this really important real estate? So you're absolutely right. Can we reuse it? Do we have to launch more and more satellites? Somebody gave me an analogy a couple of weeks ago where we do all this recycling now. You fill in all your bins, you recycle your glass, you do all that kind of stuff. Now, that's been a relatively recent thing. So maybe if they said 200, 300, 400 years ago, we'll just put all the glass to one side. And then the technology changed and it was able to be recycled. You wouldn't have all this stuff in landfills. So the material that's in space at the moment is quite difficult to get to and very difficult to reuse and repurpose because you need robots in space, you need some kind of platform to put them to. It takes a lot of fuel to move around space to change your orbit. So actually it's quite economically inefficient to do it. But there are proposals to do a number of things. There's work in the UK Space Agency and the UK government are quite keen on this to basically do in-orbit servicing. So a bit like the picture I showed you from the geostationary orbit, where we refuel satellites and we extend their lifetime. That's what they're talking about. There's ideas for more technical refueling where we replace components. That means you have to build the spacecraft to be replaceable. It's built in modular components so you can swap parts out. The Hubble was built to be modular. They were able to build, it had handholds on it for a start. So these little monkey paws could drag out components. Most satellites aren't built like that. And even for the ones that we can't build and can't repurpose, there's talk that maybe there'll be some kind of orbital scrapyard. So rather than deorbiting them, all this expensive material that we've spent building, and then even more expensive to put it at very fast velocities in space. We put it together onto a platform, and we either repurpose and strip it down there, or we leave it together, and at some point in the future, when the technology is better, we can repurpose it and reuse it. So we're not wasting all this. So there's loads of plans about it. The problem with all of it is it's got to be commercially viable. And almost all of this will rely on, at least in the early stages, government funds. There's a company called Astroscale in Cardiff who have their test satellite in orbit now, and they're looking at being able to repair, reuse satellites. There's loads of legal problems. If you launch a satellite, if I launched a satellite, a private company, got nothing to do with the UK. The UK are the ones that have allowed me to launch it. The UK government are responsible for it. I'm not responsible for it. So if anything happens in space, they're responsible. Some objects in space, we don't know who's responsible. You can't just be a pirate and go and use them. Others are from countries that just won't let us. There's loads of defunct. In fact, the most dangerous things in space are some Russian rocket bodies that keep exploding. People say, oh, I want to go and remove them from space. And the Russians say, no, they're ours, leave them alone. So there's loads of political problems. But hopefully, rather than just launching more and more satellites, we can reuse satellites, reuse materials, make better use of them. So great question, Mike. I want us to get there. It's just going to take time.
Yeah, it wasn't so much about satellites as
sorry,
the translunar
okay.
craft. Could they build that?
Yeah, so that's called a cycler. So that's called a cycler. There's been plans for cyclers to do crewed missions for years. In fact, Buzz Aldrin, I'm sure you know who he is, second man on the moon. His PhD designed a Martian cycler, so a rocket that just went backwards and forwards between the Earth. In fact, it went much further than Mars and then came back and picked up crew either way. There's ideas of doing that for the moon. So you launch a rocket, you meet it at the Earth. You've got to match the speed. You then go on board and it's got all the facilities. So you don't have to take all your life support and all your habitation. There's talk of that. The current plan, so I said Artemis 2 is going to launch crew around the moon. It's effectively going to replicate Apollo 8 that happened. Artemis 3 is going to land on the moon, and the delay for that has been there is no lander yet. There's a couple of contracts out that they're designing. One of the contracts is the Starship that I showed you, the future super heavy one. The upper stage of that is supposed to be, it's not been done yet, refuelable in space. So you launch one of the rockets that has a crewed compartment. It's clearly got no fuel in it because it's had to get into orbit. You launch lots of other rockets, up to 18, I believe is the current estimate, refuel it completely, fly that to the moon, land on the moon, fly back to Earth, refuel it in space, and it never comes back down again. So there are plans for that. We've got the International Space Station, as big as a football field, massive space station. There's also plans for a thing called Lunar Gateway, which is going to be launched in conjunction with NASA and the European Space Agency. And that is a much smaller space station around the moon. And that's planning to have a lander attached to it. So you ferry astronauts from Earth orbit to lunar orbit to the space station, and then they use the lander to go up and down, small lander. So instead of taking everything on every trip to the moon once, hopefully we'll be able to be a bit more efficient. Again, all of that is technically very difficult, very expensive, and currently theoretical. But it could work. It should work.
Exciting times.
Thank you. Yeah. So sorry for going on a ramble on your first part there.
No.
Cool.
Thank you, Mike. I'm still looking around for questions. Right at the back, and you need a microphone, please. So we've got Tony in the room.
I've been listening. Hello, thank you for that. My question might be a bit simple, but those various weights, I mean, not the various weights, the various altitudes for deorbiting, are they all based on one weight?
Sorry, they're all based on weight.
The weight of the satellite, does it make any difference? I would think it would, but I don't know.
So the biggest factor of the orbiting time really is the amount of drag it gives. So the surface area of the satellite is probably bigger. So there are ideas to put things like drag sails on them that fold up very small. And then when you want to deorbit them, you launch out this massive sail that doesn't weigh a lot, but produces more drag and catches more particles, connectivity. So it's the surface area that matters more for how quick. So the higher you are, the less atmosphere you are, which means you're getting less particles. It's slowing you down less. So it takes longer to come down from higher. And then the amount of surface area. So I think, like I said in the talk, what for lower satellites at the end of life, they turn off any propulsion. Some have propulsion, some don't, and they put the largest surface area, put the satellite sideways, or point the solar panels in the direction of travel, and just have more and more a surface area for the drag is the biggest factor.
Thank you for that. And Ian, you talked mainly about SpaceX, and SpaceX is only one of the players in these constellations. So if SpaceX are thinking about having 30,000 satellites in orbit, what about the rest of the players?
Absolutely. And SpaceX get a lot of abuse and a lot of bad press, some of it deserved. But really, they're just the first. And although they're kind of doing a bit of a land grab, a bit of, finders keepers, they get the most satellites first, they kind of occupy the space. They are just the first. They've got the first rocket, they've got the first, it's called vertical integration. They own everything from the rocket to the satellite and everything in between. So they're commercially efficient, and they've got these plans. That's 30,000 in their second generation. In fact, just this week, they've announced another 15,000 in another generation as well as. So they're already aiming on 30, 40,000. And in fact, just on pure numbers, I said there's 13,000 satellites in space. Almost 9,000 of them are Starlink from this one constellation. So over 60% of all satellites currently in orbit are SpaceX. That being said, they have engaged with the astronomical community. They've tried to do things to mitigate the problems. So the risk of collisions in space is a problem. And the rules say you have to say the risk of collision is 1 in 100,000. SpaceX naturally operate at 1 in a million, so 10 times better, again, to try and protect the environment. They built a thing called the dark sat, which they painted black to such that it didn't reflect. It got too hot and broke. They built a thing called the visor sat, which had a shield and blocked the light. Unfortunately, the shield caused more drag from surface area, like I was just talking about. So that was a problem. And now they've got mirrors. So they are working with it. They are a generally responsible operator, although the scale is unlike anything we've seen. I said, so other operators then. So Jeff Bezos, Amazon, they're a bit behind SpaceX, but they've built their own rocket and they have tested it, called Blue Origin. And that's a super heavy reusable launch vehicle. And they want another 30, 40,000 in a constellation called Amazon Kuiper. That's going. There are a few others of hundreds. In fact, the third biggest constellation, the second biggest constellation after SpaceX, with its 8,000 or 9,000, is about 700, and that's from OneWeb, which the UK government owns part of. We did actually own half of it at one point, but we've sold it off to the French and a few other people in order to get our money back. So the second biggest constellation currently in space is OneWeb provided internet, and that's at least part UK owned, certainly a European constellation. There are plans for other constellations in Europe. The European Union are planning one called Iris of hundreds of constellations. A lot of military are looking at constellations because at the moment they use satellites and geostationary. So the UK military have a small number of satellites in geostationary that are really good, really effective, but because there's only a few of them, they're vulnerable. You blow them up, there's nothing else. But if you've got hundreds, thousands, they're resilient. The Chinese have got a thing called Kuaifang, or 1,000 sails, and that is I think it's about 20,000 satellites they're planning to launch. What's even worse with the Chinese one is it's in a much higher orbit. Theirs are about 800 kilometers, which is much worse for astronomy if they're higher. And because they don't have a reusable vehicle, and even if they had a reusable first stage, there's still the upper stage. They reckon to launch the constellation, there'll be about 1,000 upper rocket bodies put in this higher orbit, and they're not particularly responsible. And there are international rules. There is space law about behavior, but they're very, very difficult to enforce. You can see in Ukraine, international laws are really hard to enforce without a big stick. So we're in the first stages of this with one company, and we've had an exponential increase in satellites. You can imagine where it's going to go when we've got 2, 3, 4 companies, 2, 3, 4 countries, different competing constellations looking for the same money. Legislation's a problem, and in fact, I'm going to the United Nations in early December to do a workshop to say, how do we build legislation that tries to at least manage and protect this? And the ITU, which gives the frequencies, maybe that's a point where we can do it to say, actually, you don't get anything to operate and transmit. It's difficult to do governance, but yeah, there's going to be a lot more, and SpaceX are just the first. It's easy to beat them, but they do actually try and help us. I hope that answers your question.
Partially. I've got a few more questions, but I will come back to you.
Oh, okay.
Simon.
Thank you, Ian. Very interesting chat. I've been reading about this sort of critical level that if you get 2 satellites that crash, and if there's that many satellites in orbit, that it'll have a knock-on effect and it will wipe everything out. Can you just explain a little bit about that and how close we are to that stage?
Yeah, so that's called Kessler syndrome, or a Kessler cascade. And if you've ever seen the Sandra Bullock film Gravity, it's basically the opening scene where a weapons test happens and it destroys a satellite, and bits of that satellite hit something else and go on and so forth. And Don Kessler, I think in the 70s, posed this as a problem. And it's exactly that. It's one satellite hits another. So I've been talking about satellites, operational satellites, and I've been saying there's like 13,000 operational satellites. There's about 18,000 satellites if you include all the broken ones. There's probably another 15 or 20,000 bits and sticks that come off the side, or components, all that kind of stuff. Beyond that, we don't even know how many, but there's an estimate of millions of objects below 10 centimeters in size that we can't even track. And that'll be things that have crashed into each other and spread out. That'll be things like the Apollo astronauts, their capsule ejected all human waste into space. So there'll be frozen astronaut piss, basically, in space, and associated other things. There'll be hammers and gloves they've dropped off from crewed missions. All kinds of things happened. And you can imagine how a small bolt that weighs a few grams traveling at 15,000 miles an hour is going to do some damage to your spacecraft and probably going to go through it. So some of the stuff we can't even track, which is the problem. What we're worried about is satellites colliding, and there has been a few. So there was a crash a few years ago between an Iridium communications satellite, an American communications satellite, which could maneuver, could work, and a defunct old Soviet satellite called Cosmos that crashed into each other, blew debris everywhere, and that caused problems. They had to move the International Space Station, basically change its orbit to dodge it. There has been other satellites that have just exploded when they're at their end of the life. The batteries have just got weak. We hear of electronic bikes, e-bikes, and cars going on fire and blowing up. Well, the same thing happens in satellites. That's happened. But we're worried about satellites there being so much in space that they're going to crash into each other. And although space is big, it's finite, particularly near Earth, because we're only caring about shells around it. There's different arguments about how much capacity we can actually put into space. Some people who have a commercial interest, Elon Musk being one of them, say that the capacity near Earth is near infinite because you just need to be able to know exactly where your satellites are and maneuver them, like you do with cars on a motorway, which is true to some extent. But the difference is you can see and you can control the cars and you know where they are. Whereas satellites in space, we have positioning, but it's not actually that accurate because orbits change, the atmosphere expands in sun, the satellites maneuver, solar pressure, the solar wind slows satellites down. So actually, when we say a satellite is in X place, what we really mean is it's in a box 10 kilometers by 10 kilometers. And then other satellites in a box 10 kilometers by 10 kilometers. And we say a conjunction, so when they're going to come close to each other, is that them boxes cross. Now, you should then move. If you can move the satellite, there should be coordination between the two different owners, and they should move the satellites, which sometimes works, but sometimes doesn't. There was a problem with the early Starlink where another provider had a satellite and was going to move their satellite. They phoned Starlink to say, what do you want to do? And nobody answered the phone. This is something that happens in a few minutes. What are you going to do? But what if you can't move the satellite? What if it's two satellites that are dead and are still in space? They're broken because everything has a failure. They hit each other. They start scattering. They start affecting other satellites. Similarly, weapons tests. Anti-satellite weapons have been tested in space. America says, oh no, it's really bad and you shouldn't do it now, to people like China and India. But then they did it in the 80s and 90s. So, you know, it's a bit hypocritical sometimes to say we've done it, you're not allowed. There was an Indian test a few years ago that was supposed to be low and supposed to reduce the debris in space the way they were doing it. Actually, we've discovered debris thousands of kilometers higher that have been ejected off kinetically. The cascade you're talking about then is these pieces will start hitting other satellites. More and more debris will be made, bigger and bigger. It'll destroy satellites that are completely far away from the original thing. It could go on for years, depending on the altitude. This could persist for years, decades, hundreds of years, depending on where you are. And it'll destroy the billions, trillions of dollars of spacecraft we have in space that we rely on, potentially. But what it could also do is make it harder for us to go to space. Suddenly, you've got to build spaceships, spacecraft launching satellites. They're a bit like tanks. They've got to be able to resist the material hitting them. There are ways to shield them, stuff like that. Again, that's heavier, that's more expensive. It becomes difficult to use space. Final point, you said, how likely are we? Well, we don't know. So there's a bloke called Hugh Lewis, who's currently just started working at Birmingham, professor. He does this kind of stuff. He did some analysis that in 2022, there was 4 million close calls with Starlink satellites being close to each other. 4 million in 2022. Then there was 3,000 Starlink satellites. There are now currently 8,000 Starlink satellites. I'm guessing this year there was, what, 10, 15 million close conjunctions in a year. If the chances of something hitting are 1 in a million, and you're close to each other 15 million times a year, those odds mean that something's going to hit. You know, we're probably lucky that it hasn't happened yet. And they do maneuver, they do avoid each other as best they can. Potentially it could happen. Would it really be as, I mean, the doomsday scenarios, we're surrounded by a shell. Have you ever seen the Disney cartoon Wall-E, where we're surrounded by a shell of waste? Yeah, my kids dragged me to it a few years ago. The Earth was surrounded by a shell of junk. That's probably not going to happen, but it will cause a lot of problems. Like I said, a satellite blew up not so long ago, and they had to move both the Chinese and the ISS because they don't take risks with human spaceflight. But satellites have to move all the time. And every time you move a satellite, you're using fuel, which means you're making its life shorter, which means you're making it more expensive. So just commercially, having all this junk could be a problem. Yeah, I hope that's answered your question, Simon.
Yeah, very interesting. Thanks very much.
Thank you, Simon. Jess Robinson, online.
Yeah, hi. It was going to be around the Kessler syndrome, but the other question I had off the back of that was, when you launch a satellite like Starlink and so, is there an insurance liability that you have to pay for? Would these cascades cost, you know, as you said, trillions in insurance claims? I guess whoever's satellite caused the damage would then foot the bill.
So there is insurance that you have to have for launch. So if you were launching something to the UK when we launched SOAR, even though it was launched,
I was going to ask you, you launched yourself, didn't you? So
yeah. So we launched on an American rocket, but we got our license and our communications license, in particular from the UK Space Agency. It's now under the CAA. I think it's been transferred over the Civil Aviation Authority. So you do have to have insurance, but it's quite limited insurance, and it's based on the cost of the spacecraft. It's more about the loss of the spacecraft. So for us, SOAR was worth 2 million. The biggest satellites that go to geostationary might be worth a few billion, but it's probably not more. You're not insured for a value more than the value of your spacecraft, rather than the effect it could cause. And ultimately, the nation state is responsible as well, so they carry the can if something goes wrong. There is, like I said, the space law. There's a lot of there's a thing called the Outer Space Treaty from 1967, and it's very much a product of the Cold War to stop the US and the USSR attacking each other. So it doesn't really work for the modern space age, but it's quite hard to change international law. But it's never really been tested. So there's a thing called the Liability Convention as part of that, which says this is who's going to pay for it, how much have you got to pay for it, all that kind of stuff. But nobody wants to be the first person to test it, because if you've got to take it to an international court, international tribunal, nobody's ever done it before. And there's been a couple of events that could have enacted the Liability Convention. The most high profile was probably in the 80s, where a Soviet satellite that had an onboard nuclear power generator called a radiothermal generator It was installed in the spacecraft upside down, the satellite. And then when it got into space, it deorbited rather than launching up. Fantastic engineering. This meant that the satellite crashed into Canada and scattered radioactive material across the wastes of northern Canada. Now, that's a claim on the liability convention. Canada had a right to raise it, but rather than doing that, they come to a nation-state-to-nation-state agreement and got paid compensation directly by the USSR of a few tens of $1 million, whereas technically they could have took it to arbitration. So at the moment, it's been at state level, it's been at low level, but the insurance isn't really covering it. And like everything, like almost everything we do that damages the environment, insurance doesn't really cover the costs. You know, extracting oil doesn't cover the cost of climate change. Using reservoirs doesn't cover the cost of the desalination of places. So it's again a difficult legal problem and one that's not thoroughly been tested yet.
And hopefully, what impacts on putting our driving insurance up? Yeah.
Well, yeah, driverless cars will do it for you. Yeah.
Thank you for the talk. Great. Cheers.
Okay, Jess.
Just following up from Jess's question, a bit parochial, but if one day I'm sitting in the back garden and something falls out of the sky, wipes out my home observatory, and I pick up a piece of the rubble and it says Starlink on it,
yeah,
am I allowed to sue?
You would have to make a claim against the United States as liability. So yes, you are allowed to sue. I'm not sure you've got enough money to make that claim against the United States. So it'd probably be a nation state to nation state thing. But yes, it is covered by the regulations. It talks about causing harm to third party nations that aren't involved in the launch. You know, it's complex legal documents. But yeah, you could sue. Whether you'd win or not is a whole other question.
Okay, I'll just come back to my last question, and we'll call it tonight then, Ian, because we've worked you quite hard. Oh, there's a question. Sorry. Before I get to my question, I'm going to hand over.
Going back to the collisions, it's one thing if a satellite hits another satellite, but will a time come when manned space exploration is more or less put on hold because you can't safely get out of Earth orbit without working away through a gap between satellites?
Yeah, that's exactly true. So I think when they were talking about the Kessler Cascade, the worst case scenario is you're going to have to army your spacecraft, in which case you're probably not going to risk sending people through it. Just launching to space now is one of the biggest challenges. So again, to go back to Starlink, because they're the first, the current deployment of Generation 2, that 30,000 satellites, has been authorized for the first 7,500. It was submitted in 2022 for permission, but it only got permission in November last year. And one of the key reasons why the permission took so long is there are so many satellites that it was hugely affecting the launch windows. So if you're going to certain orbits, you can have quite regular launch windows. You know, the International Space Station comes over quite regularly, but it is still quite limited. There are still specific times. And if you want to launch a rocket there with a person on board, you want to make sure there's no satellites going to be in your path. And you have to plan ahead. You have to say that in 500 kilometers, there won't be a satellite there when I get there. So it's quite a complex analysis. We are already losing a lot of these launch windows. So that's for crewed space flight. And that was the biggest holdup for SpaceX being allowed to increase the number of satellites they've got, is that they need to be able to coordinate and move their satellites out of the way or do some other action so that we can still get up and down to the space station when we need to, and perhaps in an emergency. Even beyond crewed space flights, some science missions beyond Earth, so things like Juno going to Jupiter, the launch window happened every 2 weeks for 20 seconds. So you had to launch the rocket in that 20-second period to make sure it got to Jupiter. Otherwise, you'd have to wait 2 weeks. And if a satellite's in the way, you've got to wait 2 weeks. And the period of these 2 weeks probably only lasted about 3 months. And then you're waiting 5 or 6 years until it happens again. So if this is constantly blocked, actually, our ability to explore the solar system beyond Earth is greatly restricted. And to go back to the crewed launch, there are plans for crewed launch to asteroids, for crewed missions to Mars. These are all going to have restricted launch windows. I think it's every 18 months you can launch to Mars effectively because they're closer. If the satellite's in the way, you've got to work out how to get around them. So it's already affecting crewed space even before the Kessler cascade, and it's only getting worse.
Okay, Henry, thank you for that. Right, last question then, and this is a personal interest. And you were talking about cheap launches into low Earth orbit, and there's been a project running for many years, since the 1980s. Its latest incarnation was the Reaction Engines company, and the Sabre engine, and
some Skylon spaces, Oxford.
Skylon, yes, coming out of the BAA HOTOL program. And the company seemed to be on the verge of getting a usable flight to low orbit, and it's collapsed. And the technology has been taken up. Do you ever see a day where that technology will mature enough to provide a space plane?
Yes, I do. And in fact, so again, to go back to the Starship that's been launched with the 100, 150 tons, there's lots of claims that it'll be able to carry 100 people, that it'll do point-to-point human launches. If you want to go to Australia from London, you can get on a Starship and it'll take you 30 minutes and it'll take you there. Like a lot of things that are made in the space sector, the claims are far outstripping the reality. And I'm sure you remember the Challenger disaster and the Columbia space shuttle disaster, because they didn't have escape modes for those astronauts. Well, the Starship landing on its tail on its rockets, a couple of failures, and suddenly that hits the Earth. You know, it's quite a dramatic thing. So I personally don't see that as being the way to get mass use of space travel. Something like the Skylon space plane is probably much more likely, and much more desirable for routine non-astronaut space flight. For people like me and you to just be able to go to space, it's probably going to be something like that. Now, the reaction engines and the Skylon system, again, there was a lot of hype about that, and the claims that it was close to actually going to doing a test probably were quite far from reality. What they did do is, because of the speeds it would have to travel at, the intake, the temperature of the atmosphere going into the intake was at thousands and thousands of degrees, and they had developed a novel, unique system to cool that, to then be able to go into a ramjet engine effectively and use that as fuel. So they had working prototypes of that part of the design. That's a long way from having a working space plane. And ultimately, they just ran out of time convincing enough investors to put enough money into them. There is a lot of money in venture capital that's been invested in things in space. Like most things, venture capital doesn't really understand what it's investing in. It goes for the latest buzzwords. So 15 years ago, it was investing loads of money in cyber, whatever that means. 5 years ago, it was investing loads of money in space. So they were throwing money at space ventures. And currently, they're throwing money at AI ventures. So they're just throwing money at things. In most venture capital, the investment 1 in 10 is successful. So 90% fail. In space, it's probably 1 in 100 major things fail. So there's a lot of money being thrown at things that may not come true. That being said, I think eventually we will have space planes. I think you can malign the space shuttle a lot, but it was the first ever space plane from 1970s technology and launched 130 odd times, I think, off the top of my head. One day we will have planes that take off from airports that you get on as if you were going on holiday, and they take you to orbit. They take you around the world using ballistic trajectories in above space. I think it's coming. How quick? I wouldn't like to bet my house on it.
Thank you for that answer, and thank you for a fascinating evening. I hope that you will come and visit us again. Ladies and gentlemen, will you join with me in giving Ian Muirhead a big Max Prince Swinton Astronomical Society? Thank you. Thank you very much, Ian.
Brilliant. Thank you for inviting me again, and thank you for your questions. It was really interesting.